Okay, let's welcome the last speaker of the session 1, Professor Jun Zhu. He is the professor at the Department of Computer Science and Technology in Tsinghua University, and the co-founders and chief scientist of the Real AI. He was a adjunct faculty at the CMU, and his research interest lies in machine learning. His talk is on the adversarial robustness of the deep learning. Professor Zhu, please.
Okay, thanks for the nice introduction and also invitation. It's my great honor to speak in this workshop. Right, so can you see my screen?
Yes, we can see.
Okay, all right. So today I want to share maybe some work on the adversarial robustness of deep learning. So I assume everyone should know some about deep network or deep learning. But today I will talk about the adversarial robustness. So this is one simple example where we suppose you want to learn a deep network to clarify images. So on the left side, I show two examples where the network can predict correctly with high confidence. But the middle column actually shows some example of the so-called adversarial noise, which are found by algorithm automatically. And if you impose this noise on top of the images, by the way, the noise was amplified. So when you actually do the create the adversarial examples, the image, the noise can be like much smaller than this. So you will see on the right column that the adversarial example actually can be for humans. Actually, we can reliably recognize the concept. However, for the same neural networks, actually they can be misled with a high confidence. So this phenomenon is called adversarial examples existing in deep networks. There have been a lot of work on this, on understanding the mechanism of deep learning and also try to protect these adversarial examples from being risky in applications. So not only in the physical world, actually in the digital world. In physical world, actually we have many examples where adversarial example can attack the real systems. So on the left side, we demonstrate a case where if you print the adversarial example like as the glass on the, for example, A4 paper, and actually we show that you can unlock some commercial phones in a very limited time. And the right finger demonstrate another case where if you use like a 3D print technique to print the adversarial noise in the 3D objects, they can successfully attack the visual and the LiDAR system for the auto-driving system. So this is the L4 L4 system on the test. So this has raised a lot of potential risk in society. So not only in computer vision, researchers have demonstrated similar phenomena in other kind of modality of data. So for example, the natural language processing, if you clarify documents, you can, for example, use algorithm to edit some words or even some characters to mislead the system. And for graph structure data, like a transaction data or other kind of graph structure data. So we also demonstrated that use similar kind of algorithm, you can change a few edges or nodes to mislead the deep learning system. And many other cases, including reinforcement learning, where you can mislead the policy to make, for example, some low reward kind of decisions, and for speech recognition, and also LiDAR recognition, even including like a 30-point cloud and code generation, a recommender system, and many others. So essentially, this kind of like different cases actually demonstrate that adversarial robustness may be a fundamental issue of deep learning, of deep networks, or even like other kind of machine learning method. So from 2017, actually, they have also another track to hold like competitions to promote the discussion, research, and technical development in this direction. So I list some example here. The first international competition was organized by Google Brain in 2017, including the algorithm attack and defense, particularly for the deep neural networks. And later on, there, including the traditional network security competitions like Jigapong, they're also interested in the AI security competition. And from 2019, we also joined forces with some industry lab to hold a security AI challenge program with several challenges online, and also we joined with some international conference to promote the research in this direction. So there have been a lot of progress in technique, so especially on the attack side, on the attack algorithms. So but today I will just show you some progress on the defense. So which can be like arguably more important than attack. So so from the we can group the existing technique in different categories. So the first one may be robust training. So like the most representative algorithm is called adversarial training. So we use a attack algorithm to identify the weakness of a network and gradually improve by retrain the network. And we also have technique to regularize the learning process to hopefully learn a well-structured manifold which can be more robust against the adversarial noise. And we also have technique to, for example, to transfer the input. Like a very straightforward idea is that can you do the denoising kind of process for the adversary examples? So there have been some work on this direction, and also progress on the randomization of the data of the feature, and also technique on the model on sample and certified defense, where you can show some probable defense over the noise in particular range. So as I said, there have been a lot of work ongoing, and this area is still largely open in many aspects. But today, I just show some example where we can understand this phenomena and try to mitigate this issue from the learning perspective. So the example I will show is the first example is on the examining the loss function we use for training a network. So there have been some theoretical analysis from the in machine learning to understand this phenomena. So here I highlight one example. So on the left side, the dataset is called MNIST, which is the very standard benchmark in machine learning, also very simple image dataset. On the right finger is on the C+10, which is more high dimensional and more complex than MNIST. So these two fingers actually demonstrate a interesting phenomena for the simple dataset, where you look at the adversarial chain accuracy and the adversarial test accuracy, and also compare to the standard test accuracy with the clean data. So you will find that for the adversarial chain and adversarial test actually are very close to each other, which means that in machine learning it means that the method is adversarial robust with good generalization ability. And also the adversarial setting accuracy is close to the standard accuracy. However, on the right side, you will see that there is a huge gap between adversarial chain accuracy and adversarial test accuracy. And also the adversarial test is far below the standard test. So this actually demonstrates that for this data set, in particular, actually, if you consider adversarial robustness, the model may be not sufficiently trained to have good performance. So this has raised a lot of questions to be addressed. So also inspire some idea to further improve. So one nature idea to improve that if you want to sufficiently train a robust model, so one idea is that you can introduce actual label data, so basically provided with human experts. Another like a more kind of like a idea, more kind of a cheaper idea is that if we can save the effort of human to label data, we can leverage our own label data that can be in some sense cheaper to be implemented. And also some work have been done in this topic. So in this work, actually, we look at the problem from another perspective. So instead of introducing actual data, can we examine the objective of the algorithm of the learning process in order to have a robust training? So in order to understand the to deeply understand or answer this question is that we need to so first of all, the intuition is that so in machine learning actually, if you even we consider the whole space as a high dimensional, but usually our data stay in a relatively low dimensional subspace, or we call it manifold. So the intuition is that if we can push the data into some local space with high density, maybe we can impact to have robustness in that particular region where when our test data come in. So this raises two related questions: how to define some density in your high dimensional space, and the second question is that how about the existing objective functions we are using? Can they induce high density? So we have some formal analysis of this phenomena. So first we define the density as so this is the common definition commonly used in physics. So we count the number of samples following in a particular region, and we divide the number over the volume. So this is the definition of density. So the most interesting case is that the most interesting insight we have is that for the common loss function like softmax currency loss, so we can understand formally. So we have some technical detail here, but I think I should skip the deviation. I just show you the conclusion we have. So we can formally characterize the density in particular region if you train the network using the current loss. So I also don't like read out these equations, but just highlight one kind of phenomena we may encounter in training. So as our goal is want to minimize the loss function. So this, as you see on the bottom side, especially the right finger. So in the learning process, actually, when the loss function go to zero, decrease, actually the training actually drives your data away from some center. So if you assume there is center, actually the 2 points actually go far away from the center. So this means that during the training, actually the density, if you consider a small region in this particular area, so the density will get decreased. So this is a very counterintuitive phenomena. So that also means that using the standard training objective cannot induce high robustness for networks. So how to rescue? So we address this problem by looking at the objective. So we found that using the softmax objective function, actually they just compare relative relationship among the logics. So they just if some kind of candidate level has high rank over others, no matter how what's the value of the magnitude, actually the softmax is likely to produce the same output. So this may give you some indirect or unimpacted supervision during the training, can lead to some counterintuitive phenomena. So we address this problem by designing a new loss function. So based on a previous analysis to show that in some cases actually we can find some optimal center to have the best robustness. So this mu star is the optimal center we can identify, and in the learning process we can drive the samples to get close to the center, essentially to aggregate among the center in order to have a high density in that particular small region. So this is the high level intuition. So formally we can characterize the density after using the new loss function. So so again, this is the detailed equation here. So I just show some insight here. So we can rigorously show that using the new loss, you can have a higher sample density in particular region, and also as a highlight in this finger, once the loss function go to 0, actually we drive the data in the feature space to be centered around this point in order to have a high density in this particular region. So from the learning theory that tell you that if you have a high density, you're likely to have better robustness. So this better robustness is demonstrated from the empirical experiment. So besides the improvement on the robustness, actually we show using the new loss objective, you can have a more efficient training process to convert. So some detailed numbers here. So the general message is that using the new loss, you can dramatically improve the robustness in different strengths of attack. So there are some hyperparameter here to set the strength of the attack algorithm. So the next example is about the adversarial training. So again, as I said, this is the most effective one in use nowadays, but there are also a lot of challenges. So this is the basic formulation of the adversarial training, where you are solving a robustness optimization problem. So the inner loop is want to identify some worst case adversarial example, then you augment the training set to retrain in a robust way. So there have been a lot of algorithms try to solve each step. So I want to highlight some issue here. One issue is on the training speed. So intuitively, because we have multiple iterations to identify the adversarial example and the retrain, so apparently this training process is more expensive than the standard training. There are some improvement on the efficiency, but generally, there can sacrifice some performance on robustness. So the second one is on the generalization of the adversarial training. So means that if you use some particular attack algorithm to solve the inner maximization step, the overall adversarial training may overfit to that particular attack. So have poor generalization to other attack algorithms. So the third one is also still larger open, that you can also see a larger gap between even you apply adversarial training, the robustness compared to the standard accuracy, there's a huge gap here. So this is the challenge the big challenges in this in adversarial machine learning. There are still a lot of research ongoing. So we provide one extension of the adversarial training, try to be more robust. So the idea is that instead of consider worst case adversarial sample in the inner loop, we consider a distribution over all possible adversarial examples. So this can smooth the loss surface and make the whole process more robust. So similar as the two-step procedure, the inner loop is learn adversarial distribution. So our loop is learn robust classifier. However, if you just solve this problem, you can simply show that actually this problem can get degenerated to the standard form. So in order to make it practical working, so you need to have some regularization effect to control, to avoid the degenerated solution. So we introduce entropic regularization to have a non-trivial adversarial distributions in the optimal sense. And so this has effect on the to characterize the diversity of adversarial example. So as highlighted on the left side, so compared to like a adversarial training, even you use a random start, you can cover a small region of the samples. However, using the adversarial distribution, you can cover a larger space of diverse samples that can make the overall training more robust. On the right side, demonstrated the loss surface of the new objective. So again, we can see most smoother loss surface compared to the standard training. So the smoothness of the loss surface actually can lead to high robustness. There's some direct relationship there. So the last one I want to highlight is on the benchmark or the empirical evaluation. So this is also important part in this direction, because so we have seen many progress in attack and defense. So usually it's like an arm race. So if you have a efficient, effective attack, maybe soon later people have a effective defense strategy against that, and then there may be more powerful attack to break the defense, and you will see this kind of the progress there. So in this direction, actually, a comprehensive evaluation is very important to understand the current state art, and also to promote the further progress. So we have one project on the still ongoing project. We developed a platform called ARIS to comprehensively evaluate the both attack and defense, and also we provide some new metrics to help people understand the advantage and disadvantage of these of different methods. And we also provide some public tools and hopefully help people to benchmark their own models or other models. So at least some algorithm we cover in this platform. So this is not the latest one, but you will see there most of the representative attacking methods have been included in. They may apply to different setting of attack using different distance metrics. And for defense, we also try to be very comprehensive on the by including the representative defense strategy. So as defense, many defense methods actually are associated with the particular data set. So we consider two popular data sets, CIFAR-10 and ImmuneNet, by providing the detailed benchmarking results there. So how useful, how to use this benchmark to promote the research? I give you one case study where it's also about adversarial training. So in the literature, actually, we identify some inconsistent results. For example, one paper actually shows that in the standard adversarial training, if you do early stopping, they can have very good results, even beat another state-of-the-art method like a TRADIS. However, in another paper, actually, they demonstrated that the TRADIS actually perform better than the standard adversarial training. So this actually raises a question. So which conclusion is right or which is wrong? So based on the benchmark, actually we can examine this kind of inconsistent questions. So here is one case we did. So actually, we using the benchmark platform. Actually, we can highlight, we can analyze systematically about for example, the key hyperparameters of the adversarial training. So in fact, we show that for different settings, as listed on the left side, for different impairments, actually, they may subtly have different in some parameter setting. So like the web decay. So usually in the standard training, this parameter may be not so sensitive. However, in adversarial training, even you have very slight difference on this hyperparameter, that can give you a much difference on the final performance. So this actually answer the question as we identified before. So the general message here we have is that adversarial training is more sensitive to the usually all local hyperparameters compared to the standard training, and also this analysis can help people to better evaluate their own performance. So hopefully can help people to standardize the training settings to have more fair benchmark. So we also have a public benchmark to evaluate the attack and defense algorithms. So people can submit their own trained model or attack algorithm to this through the GitHub platform to have the comprehensive evaluation in different settings. So to summarize, so the key message is that adversarial robustness can be a crucial issue of deep learning, especially for the safety critical applications. There have been a lot of progress on the adversarial attack, including recently there also some work on the program synthesized for automated attack. So we have one example called auto decision attack, and in particular for the defense, which is arguably more challenging. So in order to have more robust machine learning method, actually we need to deeply investigate on the learning paradigm, including the learning objectives and uncertainty of the samples, even generalization theory, and also evaluation. So we also some recent work I don't have time to cover that, for example, certified defense and also memorization effect of adversarial training. And finally, I want to mention that robustness is not like a standalone issue. It's closely related to other issues, like interpretability, privacy, and our distribution, generalization, security, and so on. So we also have a upcoming book on the AI safety from the technical perspective. So stay tuned. Okay, thank you. That's my talk.
Thank you very much, Dr. Zhu. Glad to learn more on the adversarial attack and defense for the deep learning. Okay, let's see. Any question?
Hi. Okay. I have a question, but I don't know how to raise it. Should I just ask directly?
Okay, go ahead.
Okay. Yeah, it's a nice talk. I have done also something.
Hello? I cannot hear the voice. I lost the voice.
Dr. Zhu, we lost your voice.
Listen, Zhu is offline now.
Okay. Maybe
some other
we can go another question and get back to William back.
Okay. Can you hear me?
Okay, I can hear you now.
Okay. Okay. Let me turn on my camera. Hi. Hello, Professor Zhu. Can you see me? Can you hear me?
Hello?
Yeah. Sorry, it seems like my Teams crashed.
Okay.
So I have to
go first.
rerun it. But anyway, I have a question about your density. First one, the words are all nice. I learned a lot. But for the first one, you said that density improves the robustness, but your test is just more or less based on PGD. And we know that there are some more powerful tags, such as CNW and auto tag. Have you tried to use more powerful tag to see whether that improvement of the robustness is also is real or not, as compared to other more powerful tags?
Yeah, thank you for the good question actually. Right. So CW attack is kind of like a algorithm to test the robustness of a model, especially in the white box. If you don't consider, yeah, exactly. So if you don't consider the cost on on attacking actually. So I should say every model can be broken. So including the one I show here. So for the we are considering the more interested in the black box setting, which are more practical, where using the for example the new objective, they can improve the robustness against some samples based on the transferability. So yeah, CW is a good standard to test the white box robustness. So if you really want to see that, actually, for many of the robust algorithms, including the one I discussed here, so the minimum distortion. So in that case, we consider minimum distortion. So basically, how much cost you need to pay in order to break the system. So in that sense, actually, the robust model can be better compared to other one. Yeah.
Okay, nice. But so in that case, you have some robust mechanism to prevent transferability from a shaded model to a black box model, right? Because that's commonly used to attack black box models.
Yeah, you're right. Yes. Yeah.
Okay. Okay, maybe I'll try to learn more because you have not focused on this robustness against black box model. You use PD, which is also white box attack.
Oh, by the way, so white box in the training case, your white box, but we're considering the testing.
Oh, I see.
Black box.
I got you.
Yeah. Okay.
Okay, thanks.
Yeah, sure. Thank you.
Okay. Hi, Professor Zhu. Can you hear me?
Yeah, I hear it. Thank you.
Okay. This is Jun Zhu from MSRA in Xin's group, and I have two questions for today's talk. The first question is, how do we actually define what is robustness? Because some people like your talk said that adversarial robustness is very important, and I also see other work that state that they developed some method for out of distribution robustness. So I feel it's really awkward to say that what is actually robustness, because when someday people develop some algorithm to say that they have some advanced algorithm for robustness. So how is that robustness really related to, or what is it? I would like to know if there are some formal or general definition of this term. That's my first question.
Okay, that's a great question actually. Yeah, as you said, right? So there are different kind of consideration of the robustness in different settings. So in this talk, I just mentioned on the adversarial robustness. So where the input was perturbed by some adversarial noise. So if you want to ask for a general definition, so I would say robustness is kind of a concept that that measures how your performance will change against some perturbation in different maybe in different aspects, like adversarial noise, or even for the OOD detection, OOD case, actually the perturbation from the change of distributions. And so for the for my talk, actually, adversarial robustness is deeply related to the robust optimization in the mathematical society. So we often formulate the problem as min-max optimization problem. So to consider the worst case perturbation. So yeah, so by maybe in other settings we have a we can have a different definition. Like we may consider the average case perturbation. So yeah, I'm not sure whether I answer your question, but yeah, it's generally it's kind of a slightly open in different subfield. You define robustness maybe in different ways.
Okay. Thank you, Professor Zhu. My second question is related to the difference between adversarial robustness and OOD robustness, because I used to see papers that they use some adversarial robustness method for OOD generalization, because it's quite similar, because you can just generate some adversarial examples using the input perturbations and then use those input perturbations to act as the extra data for training an OOD classifier. So I would like to know that is adversarial robustness some kind of OD robustness, or the vice versa? I'm really confused by those things. Yeah.
Okay, that's another very good question actually. Yeah, we so in my group we're also working on the OD robustness. I won't say like either robust robustness is a subtopic of OD robustness or the other one. So I view these two issues actually as closely related. So like a water example, examples actually they can be treated as like OD samples. So in fact, in one of our previous work, we developed some detectors to try to identify these adversarial examples from the OOD perspective, maybe. But in general, I mean, adversarial robustness has some other kind of properties. So especially, so for adversarial robustness, we are now considering is using the worst case attack. So like a adversarial training, we have min-max formulation. So this is not necessarily true for the OOD case. So where you may just consider the change of the whole population, right? So the distribution changes, and you may consider the impacted the average performance over there. So methodologically, maybe there are some difference there. So yeah. So in short, I don't view them as one belong to another. Yeah.
Okay. So just add to your question. So there is a specific kind of OD method called DRO, which is distributionally robust optimization, like a group DRO developed by Chelsea Finn's team. I'm sure that you have heard of them. So do you think that DRO is a specific kind of method for both OOD generalization and adversarial robustness, or DRO is specific to OOD only?
I'm not sure whether there are tests on the adversarial case.
No,
so,
they haven't.
So do you know? Yeah. So as I said, so for the for adversarial samples that we are at least in the most of the current definition, we consider the worst case kind of attack. So so including like some kind of OOD detectors we have done before, like we basically use some kind of a density estimate to try to identify the out distribution samples. So that kind of methodology is slightly different from the current most of the current practice in adversarial robustness. So for example, for adversarial training, we mainly consider the worst samples that in some sense can maybe more effective to promote the adversarial robustness. Yeah.
Okay. Thank you, Professor. I'm looking forward to more discussions in the future.
Yeah,
sorry.
Thank you.
Sorry, I have to interrupt for the 10 minute. we can follow the professor.
I have no questions.
Yeah, we can
I have no
offline maybe.
No, I plan to ask a question, but anyway, I ask later.
Yeah. Thank you.
Thank you.
And thank you again, Professor Zhu, for all this great speech and answering questions.
Thank you.